All right, so as we continue moving forward, if you get really good at this stuff, then you can move on to this next year. Maybe that's a goal we should look forward to. So this stuff, it's not that bad. Does it look that bad? Okay. So lots of information you have to remember. There's no doubt about that. So, okay, so we were going to talk about one of them, and what was that? Please refresh my memory. What was that, Grace? Okay. So C3H6O. All right. So what we could do, okay, so let's go ahead and try the triple bond, okay? So and again, you people have already expressed that a lot of this is just trial and error, okay? So you might try going down one road and say, oh, that doesn't work that way, that doesn't work. So let's go ahead and maybe start with your triple bond. Okay, so if we're going to put a triple bond here, there's only one of two elements that we can put on this side. Obviously, it's going to be carbon, but what else could you put there? Oxygen can't triple bond. Nitrogen, okay? So now that we're this far, how many more electrons does this carbon have? Yeah, so it's got one more. So who's to say that maybe we can just single bond another carbon? Okay. All right. So that carbon needs how many more electrons? Right. You know, I have something written down in my notes that I bet you, I think what I had meant to do is change this to C3H4O. I see that written down on this piece of paper that I have here. Okay, so let's just change that compound to C3H4O for now. Okay, are you following me? Okay, so therefore, how many? You correctly said this needs 3 more bonds. Let's go ahead and knock them out. Okay, so is this carbon done? Is this carbon done? Yes. So how many does this one have left? It just has one. So can we put our last hydrogen there? Well, you could, but what's the problem? Yeah. The hydrogens need to be on the outside because that's just, you could say, well, how do you know that? Well, then we go back to Niels Bohr and Albert Einstein. We just have to accept that that's just the way that it is. That's just how this would be in this compound. So if we put this oxygen here, how many does it have?
I got it. No, it's 3 C's, not 2 C's.
Okay, so here's 5. How many more triangles? Okay, is this oxygen short any? But what do we have left to do? Got a hydrogen left to contend with. There we go. So that's how you could do that with a triple bond. But this also exists with a double bond, and it's not a carbon-to-carbon double bond because carbon and oxygen can double bond as well. Okay, so throughout the course of this, and if we don't get to that problem quiz today, that's fine. I'm okay. Yes? When it was C3H6? Right, right. Oh, okay. All right. Mm-hmm. Well, and let's just go ahead and try double bonding the carbons. It doesn't have to be that way, but if we tried, oops, I already made a mistake. I was going to try a single bond. Okay. So upon doing that, so if we're double bonded with those carbons, maybe if we put a hydrogen here, and then maybe probably try a hydrogen there, that leaves us with 2 more hydrogens yet, but maybe, what about if we tried this? This, it should, yes. Well,
Does this work? For the H6?
so you're double bonding your oxygen. Yeah, I believe that would work. Yeah, I mean, the reason I say that is it does work with a double bond, but it's just in a separate spot.
So I
Okay.
can just use this and keep this? So it doesn't have to be in a line?
Well, that's really, when you look at your carbon, that's still linear. That's fine. Okay. So if we tried this double bond or single bond here, okay, oops, we got 3 carbons, don't we? Not 2. Okay. So upon doing that, let's try another carbon. Maybe that's just single bonded here. And let's see here, that's X's. Okay, so we've got 1 more hydrogen. But let's see here, things are not working out the way that they should because we needed this carbon to have 1 more. And then what about if we double bonded? Nope, that's not going to work either. But this combination works too. This is similar to Jordan, so that one's garbage. Okay? So then this double bond would work. Okay? Huh? What? What?
You said it's similar to Jordan, so it's garbage.
Oh, did you say that too, or what?
No, that's funny.
Oh. I didn't hear you. I just said, well. Okay? So another way of doing that, we know that there's an electron up there and 1 down here. Now, what we need to do is we can put a single bond on here. And then another 6. Okay. I guess this goes back to this one here. I think that does work if we now do a single bond here. Hydrogen there, hydrogen there, hydrogen there. 1, 2, 3. Okay. And there we go. For this one here, C3H6 and O, that would work. Okay. And so now if we go back to C3H4O, so do we see how this one works now? Again, it's just trial and error, trial and error. Okay? Is anybody just totally lost? Okay? So let's go ahead and try, because I was looking at this saying, oh man, that's going back to this compound here. So C3H4O. We tried that one, and there's a double bond in there. Well, No, we need a double bond here. Okay. There. I think that's probably, that may be what you had too, Jordan. I'm not sure.
Yeah.
Okay.
Well, yeah.
So let's just make sure 1, 2, 3, 4. There's our 4 hydrogens, got an oxygen, and then 3 carbons. Now let's make sure that we all have 8. This carbon, does it have 8? This carbon.
Yeah. Yeah.
Okay. And then this carbon. 4, 6, and 8. This oxygen. Yep.
Well, mine's different. I did C3H6.
Right. All right. So again, a lot of this is just trial and error, and I didn't have this wrote down. I said, well, there's got to be a way to do that, and as you can see, there is, whether it is a triple bond or a double bond.
There's like 2 ways you can like use it.
Correct. Possibly. I can't guarantee that because I'm not a general chemist, but
Like on the test, is it okay if we just write one down?
yeah. Yes. Either one's fine. Yep. 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 Probably quite a few. Okay. Is there anything else on that paper then?
Okay, for Li is trying to give it's away, right?
Is it a metal?
Yes.
Do metals want electrons? No, they do not. So it's trying to give it away.
Yes. But, Mr. McKenzie.
Yes.
Okay, so if we're trying to bond something that's in the T block, we have to go based on like if it has like 2 or 3. Like,
Well, you have to go by the negative ion. Because what, just, are you asking for an example or looking at an example or need one? Okay. Okay, so let's, okay, so what's iron bonding to? A halogen would be the easiest. Okay. Fifth. Okay. So you need to tell me, what do you want, 2 or 3? Okay. So what you're saying, we said go by the negative charge. So if this is a -2, that means that's the total. So what charge does fluorine have? Negative what? No. No. What does one fluorine have as a charge? Okay, so we wanted that to be -2, so how many fluorines would that be? 2. That's why we asked you, do you want 2 or 3? So you said 2, so that's why I said go by the negative charge, so that means iron has to have a charge of what to add up to 0? Can it do that? Yeah.
So you can choose if it has like 2, so like iron has +3 +2. That just be counting.
Yes.
Okay, and you can just pick one.
Yeah. That's why I said pick a halogen, because another example you could do is that. So now what do you think the charge of that cobalt is? Because it said go by your negative charge, which is chloride, which is -1, and how many do we have?
3.
So -3 times, or excuse me, 1 times -3 is what? So then this has to have a charge of what to add up to 0? Can it do that? Right. So that means, just like what you said in a different way, the charge is telling you how many electrons that has to give away, which is what?
3.
Correct. Now it's easy to get that confused. It has 3 electrons to give away, which are negatively charged, but since you're giving 3 negative charge, means you have 3 more positive charges, and that's why this looks the way it does.
Or no, do the CO.
Okay. So what happens? Metals are in the middle because they do what with their electrons? They give them away. Okay? So we have our cobalt here. So
Metals give them away?
yes. So how many electrons does this cobalt going to give away? 3. So we'll put 1 here, 1 here, and 1 here. So at these dots, what do you suppose you're going to connect that to? Because it's a halogen, it has how many electrons?
Oh, okay. Oh, it's all coming in together. So any metal is D, or any element is D plus, it's giving it away. So it does not need 8 electrons, it's giving all of it away.
You said confusion is what part?
Well, shouldn't cobalt have 7? No, because you can't go by the row, you have to go by the negative or plus charge. You know what I mean? Is that like just in this D plus? It's just
Okay. Now, the reason we say that is that goes all the way back to those Bohr models, okay? Because what we see happening then is when you do that for cobalt, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then cobalt is at what, 3d7? Okay. So what happens is, since this is a +3, those 2 are gone because it's an outer energy level, and it just happened to take one of these as well. Okay. You don't have to look at it in that fashion, but just know that what's happening, these outer valence electrons are getting pulled out. Sometimes it's all of them in here, but sometimes it's these 2 and then 1 more out of here. Okay. All right. So now we got 2 of the chlorines out of the way. We could put 1 more on there, because, and not only could we have to, because we've got 3 of them. Okay. Now that's done. Notice if you put boxes around all of the non-metals, each one of them has how many? And how many does that cobalt have? 0, because it doesn't want any. It wants to stabilize itself by getting rid of those electrons. Okay, so then your 5th, or however you want to look at it, okay, so what element will go in the middle?
The iron. The metal, which is iron. Shannon, you're still taking notes over there.
Okay, we're live again. Okay. Yeah, welcome back. So again, look at this. This tells you that it had 3 valence electrons to get rid of. So this is telling you it has how many? So then you'd put 1 here and 1 here. Then fluorine is a halogen, so it's in what column? Are you afraid to say it? Well, sometimes that happens, but we just need to get over that. Me, I say stupid things all the time. It doesn't stop me. Okay, you never know the next stupid thing that comes out of this mouth. Okay? But usually it's meant as in a humorous way. Like, Jordan, cut your hair. So I don't know whether that's stupid or not. But anyway. Okay, so now, there again, okay, non-metals, 80 electrons around them, metals, none. Okay, is there any more aspects you would like to go over? We don't have enough time, but it's going to be, I hate Monday evaluations, I do. But it's not going to be on Tuesday. That's just, you tried. That's just the way it is, okay? But with some of these, you got to take into account just because two of you might not do it the same way, it doesn't mean that it's incorrect. Okay? Because there's just more than one way. I don't like to say skin a cat. I just say you're going around the bar in a different direction. Oh, okay. All right. Resonance structure? No. No. I just like to introduce that, and it just means the double bond rotates around in 3 dimensions. It's either on the left or the right or on top, for instance, if it's SO3. Then if you're doing, for instance, let's say, I gotta think of an example, maybe Cl and O with a -1 charge. What does that -1 mean? You're adding an electron.
And then you could just put like the E for something.
You can put the E. That's correct. That is correct. Okay. Now, if someone's watching this, they're probably looking up at that and saying E. Either that's really confusing, or someone who's looking at that and understands that is a genius. I don't know which way you want to look at it. Okay. So. Okay. I say that to the sophomores all the time. Yeah. So if there's no more questions, I will collect them, and then the rest of the time, there's a little over 15 minutes. Is there anything else, people? Okay, we'll pick up with this problem quiz on Tuesday, and then next